Hi dear students, we discuss the next topic, that is the basic electrostatics properties of conductors. Actually, the conductors consist of a large number of free electrons, and these free electrons are free to move throughout the material, whereas in the insulator the electrons are tightly bound to the nucleus, therefore they are not free, and they are not free to move throughout the material. The first properties of the conductor, that is the electric field is equal to 0 inside a conductor. That is, if you place a conductor in an external electric field, then the electric field inside the conductor will be 0. Why this electric field becomes 0 inside the conductor when it is placed in an external electric field? Before going to the explanation, I would like to recall some of the basics that you have already learned. That is, all the material in the world is made up of neutral atoms. Neutral atom means an atom consists of a nucleus that consists of protons. Then the total charge of the proton, that is represented by positive, and the same number of electrons will also be there in an atom, and those collective charges that are represented by negative. Therefore, the number of positive charges in an atom is equal to the number of negative charges. Therefore, these positive and negative charges cancel. The atom will be electrically neutral. Those neutral atom is represented by this way. If we apply an external electric field to this atom, then these charges, that is positive and negative charges inside the atom, experience electrostatic force. The positive charge will move in the direction of the applied electric field. That force is given by F is equal to QE. That is, the positive charge will move in the direction of the applied electric field, or the negative charge opposite to the electric field. That is, this is a picture after the application of the electric field. That means there will be a charge separation. The size of the atom will not change. That is, the positive will be here and the negative will be here. And there will be an electric field induced because of the charge. That is, these induced charges create an electric field that starts from the positive charge and ends on the negative charge. This electric field is given by E prime or E dash. That is, this E dash is the induced electric field. If a conducting material consists of a large number of atoms, neutral atoms like this, and when this conducting material is placed in an electric field, then there will be a alignment of positive charges in the direction of the electric field, if this is a applied electric field, and the negative charge move opposite to the applied electric field. As a result, our conducting material, that is, can be drawn like this. This is the applied electric field, that is externally applied electric field, and charges that induced inside this conductor will be, one side will be positive and other side charge will be negative. Then the electric field induced will be from positive to negative. That electric field is represented by E dash, and this induced electric field E dash exactly cancels the applied electric field E. Therefore, the net electric field inside the conductor will be 0. E inside. That is, there will not be any volume charges. All the charges will move to the surface. Only the surface charge exists. There will not be any volume charges. That is, once the external electric field is applied, these free electrons that moves until the induced electric field cancels the applied electric field, so that the net electric field inside the conductor will be 0. Actually, if you consider the atom, the positive charges have nothing but the protons that are much heavier than that of the electrons. Actually, when we apply the electric field, this proton cannot move because of its heavier mass, but the negative charge moves in the opposite direction. If the proton still remains there, and if the electron is slightly displaced to the opposite to the applied electric field, this will also create a charge separation. One side of the atom become negative and the other side will become positive. In this way, an induced electric field E dash will be developed in the atom. We can note down here, when a conductor is placed in an external electric field E, positive charges move in the direction of the applied external electric field and the negative charges move opposite to the electric field. As a result, an electric field E prime is induced inside the conductor, which cancels the applied external electric field E. So, the net electric field inside the conductor is 0. That is the essence what we have explained here. Okay. Now let us go to the second property. That is the second property is volume charge density rho is equal to 0 inside a conductor. Just now we have seen that the electric field is 0 inside a conductor. Okay. We know the Gauss's theorem, that is del dot E is equal to rho divided by epsilon 0. Now, if the electric field is 0, if E is equal to 0, according to this expression, then our charge density will be 0, which means the equal amount of positive and negative charges are induced and they cancel each other. So, the net charge inside the conductor is 0. That is, I have written here, equal amount of positive and negative charges are induced and they cancel each other. So, the net charge inside the conductor is 0. As I explained earlier, the number of positive charges induced here will be exactly equal to the number of negative charges induced here. Therefore, the total charge induced, that will be 0. That means rho will be 0. Therefore, the electric field inside the conductor is 0. All the charges go to the surface. No charges exist inside the volume. Now let us go to the third one, that is nothing but the consequence of the above two explanation. That is, any charge, any net charge resides on the surface, which means there will not be any volume charge density. All the charges will be there on the surface of the conductor. Now let us go to the fourth point, that is, a conductor is an equipotential. Which means at every point on the conductor, the potential will be same. That is, it is said the conductor surface of the conductor is an equipotential surface. That is, from the second point, we have come to know that electric field inside the zero. The relation connecting the electric field and electric potential is E is equal to minus dV by dr. And if E is equal to 0, this will be equal to minus dV by dr. Or we can write dV by dr is equal to 0, which means the derivative of something is equal to 0 means that quantity, that is here the V is constant. That is the meaning. That means the electric potential at any point on the surface of the conductor have a constant value. That is therefore the conductor is an equipotential surface. Because as a consequence of this result, that is V is constant, means the electric field vanishes inside a charged conductor. That is, this phenomenon is called electrostatic shielding. That is, vanishing of electric field inside a charged conductor is called electrostatic shielding. That is, if the surface of the conductor has a constant potential, then the electric field does not enter into the inside the conductor. Therefore, there is the electric field will be always 0 inside the conductor. For an example, you can see one of the video that shows the vanishing of the electric field inside the conductor. That video link is given in the description of this present lecture. Now let us move to the fifth point. That is, the electric field is perpendicular to the surface of a conductor. Electric field is perpendicular to the surface of a conductor. This, when a conductor is placed in an external electric field, there will be a positive and negative charges induced, and as a result, the net electric field inside the conductor will be 0, and whatever be the charge is present in the conductor, that will go to the surface of the conductor. Because of the mutual repulsion, the charges naturally spread out as much as possible. നമ്മുടെ കണ്ടക്ടറിലേക്ക് നമ്മൾ ഇവിടേക്ക് ചാർജ് സപ്ലൈ ചെയ്യുകയാണെങ്കിൽ, ഈ ചാർജ് കണ്ടക്ടറിൽ ഡെവലപ്പ് ചെയ്യുകയാണെങ്കിൽ, ആ ചാർജുകൾ മാക്സിമം കൂളംബ് റിപ്പൾസീവ് ഫോഴ്സ് ഉണ്ടാവും. ഒരു ചാർജുകൾ തമ്മിൽ കൂടിയിരിക്കില്ല, പരമാവധി റിപ്പൾസീവ് ഫോഴ്സ് മൂലം അകന്നകന്നിരിക്കും. ദാറ്റ് ഈസ് ദ ചാർജസ് ഓൺ എ കണ്ടക്ടർ will seek a configuration that minimizes its potential energy. അപ്പോൾ ഈ ചാർജുകളൊക്കെ അവയ്ക്കൊക്കെ മിനിമം എനർജി കിട്ടുന്ന ഒരു സ്റ്റേറ്റിലേക്ക് പോകാനാണ് ശ്രമിക്കുക. അതിൻ്റെ എക്സാമ്പിൾ ഞാൻ പറഞ്ഞു തരുന്നുണ്ട്. അപ്പം അങ്ങനെ ചാർജുകളെല്ലാം അതിൻ്റെ സർഫേസിലേക്ക് പോയി കഴിഞ്ഞാൽ അവിടെ കൂളംബ് റിപ്പൾഷൻ മൂലം that naturally spread out as much as possible. അങ്ങനെ വരുന്ന സമയത്ത് ഈ ചാർജുകളുടെ ഇലക്ട്രിക് ഫീൽഡ് സർഫേസുമായിട്ടുണ്ടാക്കുന്ന ആംഗിൾ ഇവിടെ 90 ഡിഗ്രി വരും. See, ഇവിടെയൊക്കെ നമ്മൾ ചെക്ക് ചെയ്ത് കഴിഞ്ഞാൽ this angle is 90 degree. That is, what is the reason for the E is perpendicular to the surface of the conductor? That I will list here. That is, because of the mutual repulsion, the charges naturally spread out as much as possible, and the charges on a conductor will seek a configuration that minimizes its potential energy. I will explain this concept in the following way. There is the electrostatic energy of a solid object is minimum when the charge is spread over the surface. അപ്പോൾ ചാർജുകൾ ഇങ്ങനെ വളരെ സ്പ്രെഡ് ആയിക്കൊണ്ട് ഡിസ്ട്രിബ്യൂട്ട് ചെയ്യുകയാണെങ്കിൽ ഇവിടെ പൊട്ടൻഷ്യൽ എനർജി മിനിമം ആയിരിക്കും. അതെങ്ങനെ നമുക്ക് മനസ്സിലാക്കാം? That is, example is here. The energy of a sphere that is, we have seen that energy of a spherical shell or the energy of a surface of the sphere, that is equal to q square divided by 8 pi epsilon 0 r. ഇത് നമ്മൾ പഠിച്ചിരുന്നത് this was the energy of a charged spherical shell. If the charges are there on the surface, the energy is stored in the spherical shell whose radius is r and total charge is q. That energy is this one. E is equal to q square divided by 8 pi epsilon 0 r. And this is if the charge is distributed uniformly over the surface. That is, this is expression for the energy of a uniformly charged spherical shell. Spherical shell means does not have any volume. വോളിയം ഉണ്ടാവില്ല, സർഫേസിലാണ് ചാർജുകളെല്ലാം ഡിസ്ട്രിബ്യൂട്ട് ചെയ്യപ്പെട്ടിരിക്കുന്നത്. അങ്ങനെയുള്ള കോൺഫിഗറേഷൻ്റെ എനർജി കാണാനുള്ള ഇക്വേഷനാണ് ഈ ഇക്വേഷൻ, അല്ലെങ്കിൽ ഈ ഇക്വേഷൻ രണ്ടും സെയിം തന്നെയാണ്. That is, the energy of a sphere is this one at what condition? If the charge is uniformly distributed over this surface only, not in the volume. Okay, that is, I will complete here. If the charge is uniformly distributed over the surface. Okay, now let us check if the charge is uniformly distributed throughout the volume, that is a solid sphere. This is a, if the charge distributed through the surface, it is equivalent to a spherical surface, that is a spherical shell. That is, spherical shell means this is a hollow sphere. Hollow sphere does not have any volume. Instead, if you have a solid sphere and the all charges that will be distributed throughout the volume, such a configuration will have a energy. That energy is given by E or U. Here also we can write U because we have used the term U for the energy stored. That is 3q square, where q is the total charge and r is the radius. That is 3q square by 20 pi epsilon 0 r. Now see this, if I divide this 3 and 20, if I consider this is a 21, then I can this 21 consists of 7 3s. there is this U can be written as Q square divided by 7 pi epsilon 0 R. This is the energy stored in a sphere where the charge is distributed throughout the volume. This one. Now, if the charge is distributed throughout the volume, then you compare the expression for the energies. That is, if you can check this equation and this equation of the energies, the difference that appears here, here the denominator 8 is there, here the denominator 7 is there. That is, here the denominator is larger, 8 is larger than that of 7, the denominator is larger, therefore this U will be smaller. But here 7 is smaller compared to 8, therefore the denominator is smaller, therefore the energy is larger. That is, here this energy is larger than that of this energy. Why this energy became larger? Because here the charge is distributed throughout the volume. The amount of charge is same in both cases. Here you have the energy Q, same amount of charge. Here also you have the energy Q, that is the same amount of charge, but the distribution is different. In this case, the distribution is throughout the volume, but in this case, the distribution is throughout the surface only. Okay, here the surface distribution, here the volume distribution of the same charges. What is the consequence? The consequence is this one. If the charge is distributed throughout the volume, then such configuration will have larger amount of energy. If the charge is distributed throughout the surface only, then that distribution, that is surface charge distribution, have the minimum energy. What is the advantage of this one? The charge on a conductor will seek a configuration that minimizes its potential energy. Let me complete here. That is, we have mentioned if the energy of a sphere, that is the charge is distributed throughout the surface, then the energy will be this one. And similarly, if the charge is uniformly distributed throughout the volume, of the sphere, throughout the volume of the sphere, then the U will be 3Q square divided by 20 pi epsilon 0 R, and this will be approximately equal to Q square divided by 7 pi epsilon 0 capital R, and this energy is, that is the energy is greater. Therefore, which configuration will have the least potential energy? That is a surface distribution. That is, this distribution will have the least amount of energy. What type of the charge distribution here? That is, distribution is that is, the charge is uniformly distributed over the surface. Therefore, to obtain a minimum energy configuration, the charges will be spread out as much as possible, and all the charges go to the surface, not to the volume, because everybody wants to become stable, and to get the stability, the energy should be minimum. Then the minimum energy is obtained if the charges are distributed uniformly throughout the surface and not throughout the volume. Okay, that is the meaning of this one. Therefore, if the charges are distributed throughout the surface and where the charges are spread out as much as possible, and this configuration will have the electric field, perpendicular to the surface. Right. These are all the basic properties of the conductors. Next, we discuss the induced charges. What does it mean by the induced charges? If I have a plus Q charge here, I bring a neutral conductor that is represented by this one. Neutral conductor means this conductor has a neutral atoms. That is, the total charge of this conductor is 0 because this has equal number of positive and negative charges. And if I keep a positive charge near to this neutral conductor, what will happen? That is, I place a plus Q charge here, then the electric field lines, there will be emerging away from this plus Q charge, and this plus Q charge attracts this electron towards this side. That is, if you place a positive charge here, then because of the attraction of the negative charges, all the negative charges come and sit to this side. That is, we can say, if a plus Q charge, this plus Q charge means maybe plus 1 coulomb charge or 10 coulomb charge is kept here, then an equal amount of negative charges are induced on the nearer side of the conductor. This side is nearer to this plus Q charge, and an equal amount of positive charges that will be induced on the other side of the conductor. Actually, what happens here, when we place a plus Q charge, because of this plus Q charge attracts all the negative charges from all sides of this conductor towards it. Therefore, the all negative charges will reach us here, and because of the repulsion, the positive charges move away. That is, all the positive charges will go and sit on the other side of the conductor. Shortly, we will say that when a plus Q charge is kept near a conductor, equal amount of negative charges are induced on nearer side of the conductor, and equal amount of positive charges are induced on the other side of the conductor. Since the negative charges induced are closer to the plus Q charge, there is a net force of attraction between the external charge and the electric conductor. Okay. There will be an attractive force between these two. Fine, that means this plus Q charge and this conductor will be attracted because the opposite charges are nearer. This is the story of the induced charges. Okay, let me write all these factors here. That is, once again I will repeat the story. If a plus Q charge is kept here near a neutral conductor, then an equal amount, if the charge, this plus Q charge is plus 10 coulomb, then an equal amount of negative 10 coulomb charge will be developed or induced nearer side of the external charge, that is here, and opposite, that is here, an equal amount of, that is plus 10 coulomb charge will be induced. Since the negative charges induced are nearer to the plus Q charges, there will be a attractive force between this conductor and this external plus q charge. A plus q charge is kept near a conductor. Equal amount of negative charges are induced on the nearer side of the conductor and equal amount of positive charges on the other side of the conductor. It is since the negative charges induced are closer to Q, Q is the external charge, there is a net force of attraction between the external charge Q and the electric conductor. Then if somebody asks what will happen if a plus Q charge or a minus Q charge placed near a neutral conductor, then what will happen if the charge is negative, that is the external charge is negative, here this side positive charges will be induced and the opposite side equal amount of negative charges will be induced. Since the induced charges, that is positive, that is nearer to the external charge, and the external charge is a negative, therefore because of this opposite polarities, these positive and negative charges will be attracted, that is this charge will be attracted towards the conductor, or there will be attractive force between the external charge and the conductor. Okay, thank you very much.